Right, so I will start with some basics about the Qcow2 format. Basically, what data structures we have. There are only 2 of them in the format. And then after that short low-level excursus, I'll come back to the higher-level stuff. Basically, where we were at last year, 1 year ago, and what has happened since then, and what we are going to do in the next few months. Right, so why do you even use Qcow2 and not raw images? Raw images give you the performance that you want and so on, but Qcow2 gives you features. The main feature is that you have sparse images. That is, you have a Qcow2 image. When you create it, it's empty and it takes just a few kilobytes of space. And as you write data into it, it grows. Next thing that it allows is snapshots. It has 2 types of snapshots. The one is external snapshots, which basically means you have a backing file, a base file, that contains your original image, and you have a difference compared to that level saved in another file, and that's a Qcow2 file that sits on top and has this original image as its backing file. That's one mechanism for snapshots. The other mechanism is internal snapshots, where you have everything inside one Qcow2 file. And it has some different characteristics, but provides basically the same functionality. You can save snapshots and you can revert back to them. Qcow2 can do encryption, it can do compression, and oh yes, it can be used on block devices. So that's something that, for example, Ref is doing. Instead of having the overhead of a file system in between Qcow2 and the disk, you just store the Qcow2 image directly on the logical volume. And as soon as Qcow2 image grows and the space, you're out of space on the logical volume, you just extend the volume and give the Qcow2 image more space to extend. Right, so let's go into how a Qcow2 image really looks. We have 2 data structures. The first one is the reference count table, which basically tells us which areas in the image file are used and which are free, and for those that are used, by how many snapshots they are used. So here we have an example. The very first cluster, Qcow2 images are divided into clusters, typically of 64 kilobytes in size. For each cluster, it has a reference count. So, for example, the image header in this example has is referenced exactly once because it's the header. It doesn't belong to any snapshot. And then we have some image. Probably we have just created a snapshot so that all clusters are present in 2 snapshots, and we have some space that is free. The second data structure is the so-called L1 and L2 tables. While refcount tables are about the space in the image file, the L2 tables are about the space on the virtual disk. So this says if you have a given offset on the virtual disk that the guest sees, this maps it to the offset in the image file. So, for example, we read here from offset 128K, means it's the 3rd cluster. We go into the third entry in the L2 table, see that we have 30,000 hex as the offset into the image file, and we go into the image file and read that cluster. Now, if we wanted to write to the same place, and we would go again into the table, look at the reference count table and see this cluster that we're referencing is actually used by 2 snapshots. So we can just overwrite it, but need to copy it. So that we can, in our current snapshot, we write the new data, and the data of the old snapshot is maintained. So what happens, we allocate a new cluster. That's in the third row, the one that was previously a 0. So for allocating a new cluster, we go through the reference count table and search for the first 0 and just increase that. That's where we write our data. And of course, we're not referencing anymore the old cluster. So we're decreasing the ref count in the first row. And we update the L2 entry to point to the newly allocated cluster. And it's important that we do all these 3 changes in the right order. Because if you have a crash after the first one or after the second one, for example, if you have already decreased the ref count in the first row, but haven't updated yet the L2 table, then you would have a ref count table that says it's only referenced by one image, by one snapshot, sorry, but have actually 2 snapshots that reference the cluster. So if you delete that snapshot, you still have one snapshot left that references it, but the cluster is marked as free. So the next cluster allocation will reallocate it, and you get image corruption. So that's really important. You need to do that in the right order. And that's basically about the low-level part of this talk. And where were we 1 year ago? 1 year ago, this was shortly before the 0.13 release. And until version 0.12.4, we had a steady improvement in the performance of Qcow2 like this. It doesn't look like that much, but yeah, it's an improvement of about 25%. And actually, I have benchmarked this with the cluster size of 64K like it's today. 0.10 did use a 4K cluster size, and it would be about 1/8 of the performance that I have shown. So we do have a tremendous improvement there. But then we noticed that we didn't actually ensure the order that I just explained that we need to have to maintain crash safeness. So the right thing to do is after each update to the metadata, we need to put an fsync to make sure that everything is in the right order. And when we did that in 0.12.5, we had the degradation of performance again to the level of about QEMU 0 and 10. Additionally, we had just changed the default cache mode of Qcow2 to cache equals write through. It has been cache equals write back before as an exception because it was just performing too bad. That had improved enough to change the default, but of course still performed worse than cache equals write back. So all these numbers are done with cache equals none, which is what you usually use, but it's not the default of QEMU. So yeah, that was the state last year, and we had a lot of discussions. Can qcow2, can it be improved further to achieve the improvement until 0.12.4? We already have done all the obvious optimizations. So yeah, the question was asked if qcow2 can actually be improved further, or if we should do something completely new or whatever. An additional problem is that qcow2 was doing all its metadata updates synchronously, which means it would just call a usual write function of the libc to write out updates to the ref count table or to the L2 tables. That would block the CPU, the virtual CPU of the guest, as long as it's writing metadata, which obviously is bad. There's a tool, I think it's written by Anthony, which can measure this, and yeah, here's an example output of that. So the vCPU is blocked. Okay, there's an obvious solution to that. Let's just invent new formats, because what we have doesn't work and we don't feel like fixing it. So yeah, QED was the first try on that one. The idea is basically what makes us slow is the f-sync between updating the ref count table and updating the L2 table. So let's just drop the ref count table and only do an L2 table. Of course, you need another way to find free clusters then. So QED took the file size for this and just appends new clusters at the end. Then you have the problem that you need to synchronize the update of the file size against the L2 size, L2 update. So when it turned out that this wouldn't work like this, the next idea that came was to introduce a dirty flag and just say, don't rely on the file size. If it's crashed right now, yeah, we could have written some L2 entries that are not consistent with the file size. And if the dirty flag is set, you just need to check the whole image and calculate the new correct file size. Yeah, that's a major difference between Qcow2 and QED, is that QED has this dirty flag and doesn't have to keep the metadata consistent in all cases. It also has a fully asynchronous implementation, and it was I think the first format driver in QEMU that had a fully synchronous implementation, except raw, of course. Yeah, and it doesn't have a ref count table, even though it didn't really achieve its goals with leaving the ref count table out, but actually uses the dirty flag to achieve what it wanted to achieve. But it still doesn't have the ref count table, and therefore doesn't support all of Qcow2's features. Like internal snapshots aren't possible without ref counts, and compression isn't possible either. Some other features are missing because they are just not implemented. Then we have FVD. FVD is another proposal that was made. The interesting things it does is it separates the size of allocations from the size of copy and write, which in Qcow2 are both the cluster size. So in FVD, you could allocate space for a 2 megabyte cluster in the image file, but still mark, I think, 64K chunks, like in Qcow2, to be either in the backing file or in the current image. So you have allocated the big space, but you don't have to copy 2 megabytes at once, but you can copy 64K as you need. It also introduces a journal for metadata, which is an interesting concept. Maybe something that we should consider later for Qcow2 too. Yeah, new formats, maybe not the right solution, because you end up with 10 different formats, and each format implementing its own set of features. And if you want feature A from format A and feature B from format B, bad luck, because yeah, the other format just doesn't support the feature. So you don't have one standard format, but you have several specialized formats. You have several code bases that you need to maintain, that you need to test, that you need to document. And of course, it makes it unclear for users what to use, because I have here 10 different formats. Which one matches my use case best? I don't know. Right. Yeah, you need to convert images to take advantage of a new image format, obviously, because it isn't in that format yet. You need to teach external tools about the format. And what I think is the right thing to do is just take the ideas from the new formats that were proposed and integrate them into the existing formats like Qcow2. OK, today things have changed a bit since last year. And we have made big improvements. This is true for all write-back modes, which is cache equals none, cache equals write-back, cache equals unsafe. By saying that if we use a write-back cache mode, that is, we advertise to the guest that we have a write cache in the disk, a volatile write cache, and the guest will send flushes as it needs to have its data safe on the disk. Then there's no need that we have the metadata safe on disk before the guest asks for a flush. So we can just cache this in memory and write it not out until we actually have to. So yeah, as you see, we're writing out much less metadata. One of the advantages of QED that it doesn't have to write out the reference count updates mostly vanishes, because we don't write out reference count 2. It happens only, I think, every 2 gigabytes or so that you have to write out a single ref count table of 64K. So that's really not much. Yeah, and as you see, QED even performs a bit worse with cluster allocations because it just doesn't implement this kind of caching.
So how do you provide data integrity?
Sorry?
How do you provide data integrity?
Integrity? Well, we still need to maintain the order. But that's about it. We don't have to write it out all the time. So if the guest writes to the image, we just need to know where in the image file it is, but we don't have to hook it up in the L2 table and the reference count table yet. Only if the guest says flush, bring it to the disk, then we need to flush it.
But if your host crashes or you lose your storage, it's screwed, right?
No, it's not screwed. It's still consistent. It's just not up to date. So you have data loss, but not data corruption.
Like with a real disk.
Yeah, absolutely. It behaves absolutely the same as a real disk with a volatile write cache.
It's not just working, not just living in page cache and host?
Yeah, similar, yeah.
Well, yeah, you end up having a larger cache than you would, but you have the same exact semantics as a physical disk.
Right, but if you lose that cache for some reason, proof.
Yeah. But it relies on the guest flushing when you care about data integrity. So you need to have a guest that has proper flush submittance.
Not about integrity, about data loss, because it stays consistent even if you have a crash. You just haven't all of the data on the disk yet. So it might be that you lose some data that has been written to disk but has not yet been flushed. But the image itself stays consistent. Right. Cache equals write through behaves as before, obviously, because if you don't advertise a volatile write cache to the guest, we can't rely on it doing flushes. So we need to flush every time we do an update.
So you defer the updates to the flush?
In write back modes, yes.
Cool.
Yep.
So suppose the guest never flushes.
Bad luck. Yeah, it's a broken guest OS because.
Well, it's about a use case. I mean, the guest doesn't care very much about the data, and with an
Yeah, if it doesn't care about the data, it doesn't get the data if it's crashed.
quality of service with an ordinary disk, it will flush after a time. It won't keep the data in the cache indefinitely. So maybe we should flush after a time.
We can do that, yes, but it's not strictly required for correctness.
Right.
But it's
a quality of service.
it's nicer, yes, yes. We don't do that yet, but it's something I've thought of too. Yeah. Okay. What else? Yeah, some minor improvements. Before Qcow2 was doing bounce buffering with all requests, we're doing it now zero copy, which isn't noticeable when you're doing cluster allocation, but it should make a difference just with reads and writes on already allocated space. B-derived discard allows a guest to tell us that it doesn't need a given range on a disk anymore. So we can drop it and reuse that space or give it back to the operating system. Right, and this is about the future of Qcow2. So we have decided to try and take some of the ideas of the other formats that were proposed and build a Qcow3, basically. But first, we're doing optimizations on the existing format. First of which is introducing coroutines. You can think of coroutines as threads that are cooperatively scheduled. And they allow to make the existing synchronous code of Qcow2 asynchronous with very little effort. You can see on the slide, that's a diff stat for the patch that actually did it. Qcow2 in total is about 5,000 lines of code, so we touched only very little of it to make the change. The reason why it is so easy to change the coroutines is that you have only defined places where you switch the coroutine or switch context. So you can still keep on calling functions in libraries or whatever that are not thread safe. So you don't have to convert everything at once, but you can do the conversion, one step after another. Right, as I said before, the synchronous metadata updates meant that we would block the vCPU while we were writing to metadata. This is no longer the case with coroutines. The tool that I mentioned before can be used to verify that, and you don't see the blocked vCPU anymore. Throughput is more or less the same as before. And coroutines allow to introduce more parallelism by just pushing logs down further into the image format and allowing more parts of the driver to run outside logs or with final-grained logs. We can further improve the existing cache that I mentioned before, especially the write-through behavior. Because currently in a write-through mode, we're just doing, we're writing it out after each update. In each intermediate step, actually, of a request, instead of doing it only at the end of a request, which is what is really required. So if one request touches a large range in the image, we may have to update several ref counts in a ref count table, and it would be faster to do it at once when the request is completed, instead of doing it in all intermediate states. Right, what we're also doing is, if you're having an image file without backing file, and we're allocating a new cluster, but we're only writing to part of the cluster, we're reading out what's currently there, which are obviously zeros, and write that back to the image file. So we copy what's there. If we don't have a backing file, we know that it's zeros, so there's no point in doing that. So we could save this point and just write the changed part to it and be done with it. We could improve image resizing. It's relatively easy to allow shrinking too. Currently, you can only grow qcow2 images. Another open question with image resizing is what to do with internal snapshots, because that gives some interesting questions. What to do if a snapshot is smaller or greater in size than the current state. So you need to deal with that somehow. Okay, and so finally we come to a new image format version that I have proposed. Our C patches are on the mailing list for a while. They haven't received too much comments yet, so if maybe the next talk is boring, or I don't know, and you don't know what to do, go to the mailing list and give it a review. What it adds is the dirty flag that I've mentioned from QED, so that we can avoid writing to the ref count table as long as the dirty flag is set. And if you have a crash, we need to recover by scanning all the metadata and correcting it. We add zero clusters, which are basically a flag in the L2 table that say this cluster is not yet allocated in the image file, but it's zeros. Don't read it from the backing file. The use for which is if you have image streaming, you want to copy that file in. You don't want to access a remote host where you're streaming from for the zero cluster when you've already read it. But you also don't want to store it in the local image, because you want to keep the sparseness of the image. So you would just set that zero cluster flag and be done with it. Configurable ref count width. Sometimes I've heard that people are unhappy with the current 16-bit ref count table because it's wasting time. I'm not doing internal snapshots anyway. So for the usual stuff, which is backing files, and basically that's what we need ref counts for. A 1-bit ref count table, just a bitmap, if used or free, is enough. And last thing is subclusters, which takes FVD's ideas of separating the allocation size and the copy and write size, and does an allocation in, I'm thinking of 2 megabytes of default cluster size, and subdividing these clusters into 32 subclusters, which have their own copy and write state. It means that we have less metadata because obviously you need less 2 megabyte clusters than 64K clusters. A much bigger part of the metadata of an image fits in the cache then. So that's a good thing. And you have less fragmentation because you have bigger chunks. Nice side effect is that it allows pre-allocation even with backing files. Pre-allocation generally makes performance a bit better. So that's a nice thing. That's it.